Okay, let's start with something a bit, well, mind-bending. What if our entire universe, everything we see out there, has an expiration date, and not trillions of years from now, but maybe only 33 billion years in total?
It's definitely a perspective shift, isn't it? Throws the old ideas out the window, potentially.
Exactly. So today we're doing a deep dive into some really fascinating new research and some preliminary data, too, that suggests the end might be closer and maybe, well, a lot more dramatic than we used to think.
Right. We're talking about findings from these huge galaxy surveys, plus a new theoretical paper. It really challenges our basic picture of dark energy.
Yeah, our whole mission today is to unpack this. What could it mean? How did scientists even get to this surprising prediction? And maybe most importantly, what should you make of it all right now, ready to explore this?
Let's get into it.
Okay, so for a long time, the standard picture, the dominant idea about how the universe ends, involved this thing called the cosmological constant. And that painted a picture of just endless expansion. Right, speeding up, getting emptier, colder, forever. Kind of the simplest outcome, maybe.
That's basically been the standard model for, decades now?
Yeah.
The idea is dark energy, this mysterious force, is accelerating the universe's expansion.
Right.
And the simplest explanation was always the cosmological constant. It's just a number, really. In Einstein's theory of general relativity, a constant outward push, meaning things just keep accelerating forever.
Okay, so that's the baseline, the simple constant push. But now, well, here's where it gets really interesting. What are scientists actually seeing now that makes them think, maybe it's not so constant after all?
Well, that's the core of it. We're getting new evidence, or at least hints, from these massive surveys. You mentioned the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI.
Okay.
Their early findings, and I stress early, they're suggesting that dark energy might actually be changing, evolving over cosmic time.
Changing? Okay, that sounds like more than just tweaking a number. If these DES and DSI observations, these preliminary hints, hold up, why is that such a potential, paradigm shift? What's the big deal?
Oh, it would be absolutely huge, monumental, really.
Mm-hmm.
Because it would mean that simple cosmological constant model, the one we've kind of relied on, it's just wrong, or at least incomplete.
Wow.
It's not just fine-tuning. It suggests dark energy, this thing that makes up, 70% of the universe, might be dynamic. It might be evolving. Maybe it interacts in ways we haven't even thought of.
So it forces a rethink of the fundamental rules.
Exactly. It throws open the door and asks, if it's not constant, then what is going on? What else could it be?
And a lot of, there's a new theoretical model trying to answer that exact question. There's this paper, you mentioned it's not peer-reviewed yet, but it proposes a more complex picture for dark energy. Like it has two main parts working together.
That's the idea. This model suggests what we call dark energy isn't just one thing. It's potentially two things. First, something called an axion.
An axion.
Yeah, it's a hypothetical particle, super, super light. The theory is it kind of soaks the entire universe, like an invisible field everywhere.
Okay.
And its average energy, this model proposes, is what's driving the current accelerated expansion we see.
Got it. So that's part one. What's the second part?
The second part is still a cosmological constant, but, and this is the key twist in this model, it has a negative value and a lower one.
Negative.
Yes. So the axions are doing some of the work of expansion now, which allows this negative constant to be hiding in the background, so to speak.
A negative cosmological constant? Okay, my brain immediately goes to opposite effect. Sure. So how do these two things, the axion field and this negative constant, supposedly work together? What's the interaction?
Well, what the researchers found, looking at the DSES and DSI data, was that the best fit seemed to come from having these axions working with a negative cosmological constant. The idea is that over billions of years, these axions, they dilute. They spread out as the universe expands, and their energy density drops. They basically lose steam.
Okay, they fade out.
Right. And as they fade, this underlying negative cosmological constant starts to take over. It becomes the dominant force, shaping the universe's fate.
So if this negative constant does eventually take charge, what does that mean for the end game? You hinted at a big crunch, which sounds familiar, like an older idea making a comeback.
Exactly. A negative cosmological constant would do the precise opposite of the positive one we usually assume. Instead of speeding things up, it would put the brakes on. It would decelerate the expansion.
Slow down, stop it.
And then reverse it. The universe would stop expanding and begin to contract. Yeah, the big crunch idea isn't new, but what's interesting here is how this new data, if it holds up, And this axion model could potentially make it a serious contender again.
Wow. Okay, paint a picture. What does a big crunch look like in this scenario?
Well, you can think of it like the Big Bang played in reverse. A mirror image, almost.
Yeah.
As the universe contracts, gravity pulls everything back together. Galaxies would start merging. The whole cosmos gets smaller, hotter, denser.
Sounds intense.
It would be. Ultimately leading back to a singularity. A point of, theoretically, infinite density and temperature. Very much like the conditions we think existed right at the beginning. A complete cosmic U-turn.
Okay, and this is the part that feels immediate, almost. The timeline. We think in human scales, maybe planetary scales, but cosmic time is vast. What's the schedule for this potential crunch, according to the model?
Well, according to the paper, the beginning and the end, so when the expansion actually starts to slow down, could be only about 10 billion years from now.
Wait, only 10 billion? The universe is already almost 14 billion years old.
Exactly. It means the slowdown could start in less time than the universe has already existed.
That's surprisingly soon on a cosmic scale. And then what? How long does the collapse take?
The model suggests the collapse itself would take roughly another 10 billion years. So the universe reaches its final, ultimate crunch after a total lifetime of just over 33 billion years.
33 billion total.
Which implies, if this model is anywhere near correct, that our universe is already, as they put it, well over halfway to its maximum size. We're kind of in its cosmic middle age, potentially.
Okay, deep breaths, everyone. You might be thinking, is this it? Is the science settled? Are we heading for a crunch? It sounds incredibly dramatic. What's the reality check here?
Yeah, this is really, really important context. We absolutely have to stress that this idea is deeply hypothetical.
Okay, hypothetical.
Very much so. Remember, the DAS and DKI results are preliminary. They might not hold up as more data comes in or as the analysis gets refined. That's just how science works. Rigorous testing, peer review, checking, and double-checking.
Right, the process takes time.
And even if
Yes.
even if we do find solid evidence that dark energy isn't constant, that the simple cosmological constant model is wrong, that doesn't automatically mean the specific axion plus negative constant model is the right answer.
Oh, okay. It's just one impossible explanation among maybe others.
Precisely. It's one theoretical attempt to make sense of potential anomalies in the data. There could be other explanations entirely. So, bottom line, it's fascinating, it's thought-provoking, but we really just have to wait and see what more research tells us.
Okay, so let's bring it together. Today, we've taken a deep dive into some provocative new cosmological hints and one quite specific theoretical model that flows from them. And it suggests a universe with maybe a much shorter, much more dramatic life story than we thought, potentially ending not in a cold whimper, but a hot big crunch in, well, just over 33 billion years from the beginning.
But remember, this is science right at the cutting edge. It's driven by preliminary data, pushing boundaries. It really shows how our understanding of the cosmos isn't fixed. It's always evolving, always challenging assumptions. It's a great example of the scientific process in action, really.
Absolutely. So here's a final thought for you to mull over. Thinking about this new timeline, even if it is hypothetical for now, does knowing the universe might have this surprisingly shorter lifespan? Does that change how you think about our place in it all? Our tiny moment in this vast, unfolding, and maybe even collapsing story? Something to ponder next time you look up at the night sky.